Today we're going to look at how we can model different real-life situations using exponential functions and logarithmic functions. So we have a bunch of things that use exponential and logarithmic functions. You can add pH scale. Have you been studying that in chemistry? Yeah. Oh, don't say that. Okay. So we got population, compound interest, decibels, Richter scale. For example, well, we'll do some examples with the Richter scale and decibels, but what happens with the Richter scale is every time you go up by one, so they say one earthquake is a 6.2, another earthquake is a 7.2, well, that 7.2 is quite a bit bigger than the 6.2. In fact, it's 10 times more intense. And then if you went to an 8.2 is 10 times more intense than a 7.2. So if you would compare a 6.2 to an 8.2, the 8.2 is 100 times bigger than a 6.2. So on a Richter scale, things increase exponentially. And even though they only increase the number by one, that increase of one goes up by a lot. Same thing with decibels, but for decibels it's every 10. So if you go up from 100 to 110, that's 10 times louder. And 110 to 120 is another 10 times louder. So if you're at something that's at 120 decibels compared to 100 decibels, you've got 100 times louder sound. And then we also have some things that decay. In biology, there's certain bacteria that decay. There's radioactive substances that have a half-life that decay. And so that also looks at some exponential functions. So we'll look at a bunch of these examples throughout. We're going to start off with compound interest. Now we saw this formula already earlier, but we only used our graphing calculator to solve. Now that we have logarithms, we can solve these algebraically and use logarithms to solve for them. But to start off, there's some straightforward questions. Find the final value of $500 after 10 years if it's invested at a rate of 2.25% interest and compounded monthly. One of the things in the exponents and logarithms unit is you can get a word problem from any situation. There's no formulas on your formula sheet, and what they'll do is they'll give you a question like this and then add this formula to the question and explain what everything means. So you have to be able to interpret a formula and know where to put everything in. So you have your formula, you read what everything stands for, and here we've got final value of $500, so $500, I'll write out the formula above. $500 is your initial investment, that's your principal. Invested at a rate of 2.25% interest, so we need to change that to a decimal. Compounded monthly, N stands for how many periods per year it's compounded, so that would be 12 for 10 years. So in this case, we want to solve for A, the amount. It's not an exponential. We do not need to use logarithms. In fact, we can type this entire thing into our calculator all at once. So 500, just as we see it, bracket 1 plus 0.0225 divided by 12. Because it was compounded monthly, and if we go back to our formula here, the N stands for the number of times that it's compounded per year. So monthly means it would be compounded 12 times per year. If it said daily, you'd put in 365. If it said, sometimes it says weekly, then there's 52 weeks in a year. So after we type that in exactly and push enter, we find out the amount is $626.03. So if you had $500 and you found an account that paid 2.25% interest, which right now is a high interest rate, you could wait 10 years and make $100. Whoa. Now, I'm not sure if that would be the other thing you have to take into consideration is, yeah, you would have $100 more, but in 10 years, probably everything's going to cost that much more. So maybe that's not that much. I want you to try the next couple on your own. So one, yeah, just try this next one on your own. Did you get $232.11? So depending on your calculator, if you have a calculator that has math print like mine, you can type it in exactly as you see. But I came around and some of you have the older version of the calculator. You're going to need to put extra set of brackets around your exponent because otherwise your calculator will just put one of those numbers to the exponent. So if you were getting a different answer than this, make sure you find out how to type it into your calculator, right? Because calculators are good if you know what numbers you can push into them, but if you don't know how to use them, they're not very helpful. So the next question we're going to look at, yeah? Yes. No, and you could put 10 if you'd like to do the mental math and put it in there right away. Calculate the time it would take for an investment of $30 to double. So we have an initial amount of $30. We want it to double, so we want our amount later to be $60, compounded at an interest rate of 7% monthly. And we want to find out how long, so we're trying to solve for t. And so this is the first one that we're going to need to use logarithms to solve for. In the past, you typed the left side into y1 and the right side into y2 and found out where they intersected, which is a great graphical way of solving that, and that can be very helpful, especially next year in the IB exam. But on your exam this year, they're going to be expecting you to solve it algebraically. So we need to use logarithms to solve that. Now, in any situation that you have to use, you can use logarithms. You could take the log of both sides right away. However, if you can see something that would simplify your equation, I would recommend doing that first. In this equation, could you see that you could divide both sides by 30? If you divide both sides by 30, this becomes 2 equals 1 plus 0.07 divided by 12. The 12t. If we do that, that'll make our life with logarithms a little bit easier. We're solving for something in exponent. We can take the log of both sides, or natural log. Are you okay if I bring that 12t out in front already? And one of the reasons that we divide both sides by 30 to begin with is so that we can bring out this exponent of 12t out in front, because technically this 12t would have been here, right? And it got moved out in front. Whoa, there it is. A little bit of bounce off the G. We can only bring that exponent out in front if that exponent is to the entire base that's inside the log. And had you taken the log at the beginning, can you see that that exponent is not to the 30? But you might be tempted to bring it out early. Now that t is outside, we just have to get t by itself. 12 is a number. Log of 1 plus 0.007 divided by 12 is a number. How do you get those numbers to the other side? You just need to divide. So if I divide this side by 12 and this side by the same thing, I get t by itself. No. The quiz is on 5.4 to 5.6. So we go to our calculator, type this in exactly as we see it. Log of 2 divided by 12 log 1 plus 0.07 divided by 12. Oops. And again, I forgot. I made a minus sign. Second entry. I'm going to fix that. It should be 1 plus. How did I know right away that my answer was not good? And what would be problem with a negative? Negative time. It's going to double 10 years ago. Okay. Okay, 9.93 years. So I'm going to store this as x, because the nice thing about exponential equations is that rounded correctly? Yes, it is. The nice thing about exponential functions is after you've solved it, you can plug it back in and see if it equals what it's supposed to equal. So my original equation on the left side is 60. On the right side is 30. I'm going to go 30, bracket 1 plus 0.07 divided by 12, bracket to the exponent of 12, and I'm going to plug in x. If this is equal to 60, then we know that our answer is correct. Yes! And so it'll take almost 10 years for this to double. For $30 to go to 60. Okay. So what I'm going to do now, zoom. I'm going to just show you, wow. I'm just going to show you make that smaller, still can see it. So we did that by simplifying it first. Now sometimes you're going to get overexcited. I know these logarithm equations are very exciting. You're going to see a question like this and say, I'm solving for t in the exponent. I know I have to take logs. I'm going to do that right away. And you do the very first step that you do is you take the log of both sides. That's not wrong. It's just going to take us a little bit longer. At this point is what the reason why simplifying it first is nice is because at this point is where students make the most common mistake. You want to bring the 12t out in front, right? And that's the whole reason you take the log of both sides. However, in this situation, you're not allowed to bring that 12t out in front because that 12t is an exponent only to this. It's not an exponent to the 30. Does that make sense? That exponent of 12t is only to what's in brackets. That exponent does not apply to the 30. There would need to be an extra set of brackets around the whole thing for that 12t to apply to everything. And so what we have is we have our log law with multiplication happen first. And part of the reason that we spent so much time practicing log laws and expanding completely was to be able to recognize situations like this. So we would first have to say multiplying inside of a log is the same as adding. And now you'd be allowed to bring that 12t out in front because now that exponent is to the entire base inside of that log. 0.07. So how do we solve for t? Well, we move everything over to one side that doesn't have the t in it. And finally, divide both sides by 12 and log of 1 plus 0.07 divided by 12 to get t by itself. Now, if we take our blue equation and expand it again, I want you to look at those two right there and see if you can see why they're the same using your log laws. The numerators are the denominators are the same, but the numerators are different. But why are they equal?
Because it'd be 60 divided by 30.
Yeah, if you use your log law that says subtracting is dividing, you could divide and get 60 divided by 30. However, if we look at all of our work all the way through, can you see how much more writing you had to do if you didn't simplify first? So this first step of simplifying is really important. Okay, that's not what I wanted to do. What just... Okay. Now that we've solved this in two different ways, obviously I like the blue way better because it simplifies things early. I also like the blue way better because it points out something. This person had $30. They wanted to double it. They got a very high interest rate of 7% and found out it would take 10 years to double. And so you kind of laughed a little bit because like, ooh, 10 years later you had 30, you have $60. Okay? Now, what happens if I started the question and had 30 cents and I doubled it to 60 cents? Would I still get the second line of my equation? Would it be the same? Because what did I do from line 1 to line 2? Divided both sides to simplify. So now I would have to divide both sides by 30 cents. And I had 60 cents on the other side. Would it still become 2? Yes. And so everything else would be the same. And so if you had 30 cents in your bank account and you were getting 7% interest rate, 10 years later you would have 60 cents. Now, if we take these numbers again, and I've got room to add another 0, and let's change the units to millions of dollars. You have $300 million. You find an interest rate of 7%. How long before you have $600 million? 10 years. So the way that interest rates work is it doesn't matter how much money you have, the amount of time it's going to take to double stays the same. Now, if you do have $300 million, right, and it'd be very nice in 10 years to have $600 million, an extra $300 million. Divide that by, that's like making $30 million a year. So I've been trying, it hasn't worked yet, just trying to find someone who would just like, hey, would you mind if I hold $300 million of yours for like 10 years? And then I'll give it back. But nobody has been willing to do that yet. I keep trying, right? Because if I could get someone to just say, here's $300 million, you just have to give it back in 10 years, well, then I could find an interest rate and make, if it was 7%, that'd be amazing, but I could make $300 million with $300 million in 10 years and then give them back, and I'd be like, thank you very much. And life would be good. But unfortunately, it's hard to find. Maybe I should put a Kijiji ad. That might work.
Honestly, buy a bunch of cars on dealdash.com, sell them.
So, but this also shows where, the world is a little bit unfair. Well, not unfair, but unjust. I don't know, maybe. In that, if you have lots of money, you don't have to do anything and you'll get lots more money. But if you don't have a lot of money, the interest rates are the same. They're fair because they're the same for everyone, but the rich get richer and the poor. So, okay. Now, the other thing I want to teach you about this is something called the rule of 70. The rule of 70 looks like this. And sometimes it's called the rule of 72. It just depends which mental math is easier. So in our question, we had 7% interest, and we did a lot of works with logarithms, and we found out that the answer was 9.93 years for it to double. The rule of 70, or the rule of 72, is a quick way to estimate how long it's going to take something to double. The I stands for the interest rate, just as a regular number. We had 7% interest, which is easier mental math. 70 divided by 7 or 72 divided by 7? 70 divided by 7. What's 70 divided by 7? 10. How long did it take to double? 10 years. If you would do the same question and change your interest rate to 8%, this one's easier to divide. 72 divided by 8? 9. It would take about 9 years to double. Right? If you got 10%, this one's easier to use. 70 divided by 10? It would take 7 years to double. And the rule of 70 or the rule of 72 is just a quick mental math way to figure out how long it would take something to double. Well, why it works is some complicated math. Okay? But it's pretty cool that you get such a simple formula that comes out of, look at the math we had to do to get our answer. And it'd be like, oh, I just take 70 and divide it by the interest rate, and that's close enough for me. And this one is really close, right? 9.93. So depending on the interest rate, how high or how low it goes, the formula becomes more or less accurate. But for most interest rates, it does appear to be quite accurate. Okay, so now there are 3 more compound interest questions there. I'd like you to do those right now. I will put the answers up in a bit. So we plug everything into the formula. The p is not an exponent, so you don't need to use logarithms at all. You just need to divide to get p by itself. Plug that into your calculator, and you should get $2,049.37. Now the question is, where did Andrew get those 2 pennies? That's what I really want to know. Plug everything into the equation. I decided to take the log of both sides right away. You could have divided both sides by 200 to begin with to simplify it, which in the way that I did it, I have multiplication here, so I have to add using my log law first before I can bring that exponent of 4t out in front. Get t by itself, plug that into your calculator, and you will get 30.66 years. And for this last one, again, plug it in. It doesn't matter how much money you put for it to triple, because when you simplify it, you're going to get 3 on the other side anyways. And then you can take the log of both sides, solve for t. You can put any number. If you put 60 and 20, when you divide both sides by 20, you're going to get 3 on the other side. So sometimes on the final exam, this type of question does come up on the final exam, and people get stuck because they're like, I don't know how much money. Well, it actually doesn't matter. So that's one of the things you need to know, that you can put any amount in there. I like to think of this one as $1 million. And it would only take you 22 years to get $3 million in the end. Then that would be very exciting. And that's at 5% interest rate, which is still really high for these days. Continuous growth. Now, I want you to imagine compound interest formula, and if it's compounded monthly, that means you get paid interest every month. And if it was compounded daily, you'd get paid interest every day. And then on day 2, you would still make a little bit more money on the interest you earned in day 1. And then imagine what would happen if you kept changing the compounding period. Said, what happens if the bank paid me every minute? Just a tiny little bit every minute, and then I'd make money on that. And then what would it be like every second, and then every millisecond? And eventually you get to this idea, what happens if the bank continually paid me interest? So my bank account, I could just see it increasing all the time. Okay? And this formula, the compound interest formula, changes to this formula. So right now we're just going to explore a little bit on our calculator with this idea. 1 plus 1 over 1 to the n. If you plugged in 1 for n, what would you get? N is equal to 2. If you plugged in 2 for n, you would get 1 plus 1/2, 1.5 squared. You would get n equals 1, it's equal to 2, and n equals 2, it's equal to 2.25. Now, if we think about n being a very, very big number, 376 is a very big number, but it's not even that big. There's even bigger numbers than that, right? If you put in 1,403,000,000, right, what does 1 over 1,403,000,000 equal about? What's it very close to? Well, this part here, 1 over 1 trillion, it's pretty much equal to 0, right? And then if you went 1 plus 0, you'd pretty much get equal to 1. And what's 1 to any exponent? 1. So our brain can logically think that through in saying that if n was a very big number, then 1 over n should be close to 0. And then I would get 1 plus 0, which would be close to 1. And 1 to a very high exponent should still be 1. But I want you to play with your calculator because this does not work that way. Because even though 1 over a trillion gets close to 0, powers are more powerful than dividing. And so put in a very large number for n. Put in 1,000,000 and do 1 plus 1 over 1,000,000 to the exponent of 1,000,000 and see what it gets close to. What answer did you get? For same number. So try a very large number for n. And tell me what this gets close to. Whoops, I'm cheating a little bit. 2.71828, okay. So someone did a very large number and they got that. What does that remind you of? That's E. Okay? So this part of our formula changes to E. Did you do the exponent part? Can't even see it all?
Oh, never mind. I know what you want.
I'm not sure what happened. Oh, yeah, it should have come out to be E. It might have been that you went too big and it got. So what we're going to do is we're going to do part B here first. If it was compounded quarterly, you could plug in all of those numbers, 5.5% interest, 10 years, compounded quarterly. You would get $3,453.54. So not bad. You would have made $1,453 in 10 years. That's pretty good. What does your gut say on the right-hand side? If it was compounded continuously, how much? It's going to be more, right? How much more do you think it's going to be? Like a lot more? Or like $1 more? How many people think it'll be more than $100? Okay? How many people think it's less? Okay, you have to decide. You can't just be on the fence here and not put your hand up. Okay, I want you to get a sense for what your gut says. If you make, just as only being paid interest 4 times a year, okay, you make $3,453. This is getting paid interest all the time. How much money do you think is going to be on this side? You think only $1 more? You think $100 more? How many people I think like more than $1,000 more? Yeah? Okay. I mean, you're getting paid interest all the time and you're making money on your new money all the time. $13 more. Which is kind of disappointing. Because, you know what, your gut is saying if it's always happening all the time, shouldn't it be a lot more? Actually, no. And so this is something to understand with interest and interest rates. The actual amount of compounding periods, yes, it does make a difference. Most banks pay interest monthly, and that's better than getting paid interest once a year. However, the biggest thing that affects an investment is not how many times it's compounded, but the interest rate. So I'm going to just type in this 2,000. So we have 2,000 bracket 1 plus 0.055 compounded quarterly. $10. So there's our answer that we got from before. $3,453.54. And I want to show you that if you can get a different interest rate, so another bank account offers only 0.5% higher, so 0.06, how much of a difference would that make? A lot more. That's only 0.5%. If you find another percentage higher than that, 7%. Oops. Another $400 more. The interest rates make the biggest difference. And we're going to look at some examples later that hopefully can save you thousands and thousands of dollars over your lifetime. An investment of $200 is compounded continuously. So when you see the word continuously, it used to be that formula, which I like to call the PERT formula, with the ERT, P equal ERT in it. That used to be on your formula sheet. So you used to have to be able to recognize that when a question said continuously, you had to use the PERT formula. Now that formula is not on your formula sheet. And so in a question like this, you would have been given the formula. So knowing that the formula is A equals PERT, you plug everything in. We want to find the interest rate, which is R. R is in an exponent. So how do we solve for things in exponents? We need to use logarithms. Now in this case, since the base is e, I'm going to take the natural log of both sides. So I simplify it first, take the natural log of both sides, my exponent can come out in front, and you get the natural log of e by itself. And the natural log of e is equal to 1. Then it's just straightforward math to get r by itself. Plug it into your calculator. And again, I would store that answer to my calculator and plug it back into my original equation. Every time you have an exponential equation, you should plug it back in and check to see if your answer matches up. So there's one more question at the bottom I want you to try. Yes, you have a question in this one. Why can't you use a log law? This one? You could expand it. It would just mean that you would have to write out more stuff. So if you wanted to write natural log of 235 minus natural log of 200, you could. But you don't need to.